Hello everyone, my name is Konstantinos and today I will talk about our paper named Learning Sampling Distribution using Local 3D Workspace Decomposition for Motion Planning in High Dimensions. These works focus on the motion planning problem and specifically sampling-based planners. Over the last years, several sampling-based planners have been developed and we can use them to solve problems as the one shown in the right. For example, we can find very fast a path for the problem shown here where the Baxter robot moves its 7 degrees of freedom arm in a table with few obstacles. However, sampling-based planners perform poorly on examples as shown on the left. Here, the planner has to traverse a very narrow area in the workspace, which in this case translates to a small area in the high-dimensional configuration space known as narrow passages. Since classic sampling-based planners are informatively explore the space through uniform sampling, the probability of sampling on these narrow passages is small, leading to poor performance. So in this work, we try to improve the performance of sampling-based planners using learning, and specifically by biasing their sampling distribution. In other words, we want to go from a situation like this, where we have no prior knowledge and we are forced to plan from scratch, needing a lot of time, to a situation like this, where we can leverage previous motion planning problem solutions to solve it faster. And there is a good argument to be made that learning methods can be used for robotic motion planning, since robots usually operate in similar environments, and existing planners can be used to generate data. So first, we formulate a learning for motion planning problem. In this work, the input will be a workspace description, while the output will be a sampling distribution. We need to find a model that learns to map workspace description to biased sampling distributions that target narrow passages in the configuration space. This mapping, however, is highly discontinuous and multimodal, since the same or very similar workspaces can have drastically different solutions. For this reason, in this work, as a learning model, we have used an experience database. By using a similarity function, we can query the database for similar workspaces and apply the retrieved biased sampling distributions to the new problem. With such a pipeline, we only need a similarity function that compares workspaces between them, and we do not need to explicitly approximate the discontinuous and multimodal mapping from workspace to configuration space. However, storing and comparing all the global workspaces in the database is not very practical. That is why in this work, we are using a database of local workspaces and local samplers. The basic idea is that we first decompose the workspace to local workspaces. Then for every local workspace, we create a local sampler, and when we are given a new workspace, we retrieve from the database the local samplers, which then get synthesized in a global sampler. And here you can see the parts of this pipeline that are happening during learning, noted with red, and during inference, noted with blue. Decomposition is necessary both during learning and inference. The idea of local workspace and local samplers was introduced in our earlier work. However, it only applied to 2D workspaces with circular obstacles, and the database had to be exhaustively created a priori. For geometric object representations, the decomposition is pairs of objects that are close together. Each object is represented with its position, orientation, and size. We have 2 objects in every local workspace, which means that we have 2 positions, orientation, and sizes, one for each local workspace. For sensed environments, the workspace is represented as an octagon, which is an efficient way to represent an occupancy grid, which we decompose into a local occupancy grid which has 64 voxels. During training, we are given a solution path and the corresponding workspace, as seen in this video. We want from the single path to extract the samples and their associated local workspaces. To do that, in this work, we have devised a simple procedure to associate critical samples with local workspaces. First, we simplify the solution path and heuristically find critical configurations. Then we associate each critical sample with a local workspace. This procedure is visualized on the video on the left for geometric environments. The basic idea is that we associate each critical configuration with a local workspace that is close to them based on workspace distance. The same idea is shown for the sensed environments. Here, we associate the local occupancy grids with configuration samples when the robot at that configuration intersects with the local occupancy grid. Now we have extracted local workspaces and critical samples, as seen on the top left. Combine them in a Gaussian mixture model. Note that for the same local primitive, many critical samples can be found and associated with it, which leads into a multimodal sampling distribution. During inference, we need to retrieve the relevant local samplers by finding similar local workspaces in the database. Thus, we need to define a similarity function over these local workspaces. Geometric local workspaces, we first define the similarity over two geometric objects, which is the weighted distance of their position, their orientation, and their size. To compare pairs of objects, we simply compare the two possible combinations and keep the minimum one. For occupancy grids, we simply check if their position is the same in space, as well as if they have the same occupied voxels. Now that we have a similarity measure of local workspaces, we can use an efficient nearest neighbor structure to perform retrieval. Finally, after we have retrieved the relevant local samplers, we combine them, as you can see, with geometric and sense representation into a bigger Gaussian mixture model. Overall, here you can see how these frameworks work when a new environment is presented. The videos show the retrieved local workspaces with red and the corresponding retrieved samples as robotic configurations. Retrieved samples as robotic configurations. We have named Spark the framework that works with geometrically known environments, and seen in the left video, and Flame the one that works with sense environments, shown in the video on the right. In the first experiment we did, we assessed how good these frameworks perform on workspace changes compared them with other methods. We designed a realistic and challenging scenario where the robot has to pick a cylinder from a shelf, the one that is furthest back. To generate different problems, we vary the X, Y, and Z axis of the shelf and its angular position relative to the robot, as seen in this video. Since this is a mobile-based robot, it can approach the shelf from multiple directions, as we consider such variations realistic. In the video on the left, you can see different motion planning problems generated with this procedure. And you can see how different these motion planning solutions are even when we have slight variations in the workspace. On the right figure, you can see the total planning time on the y-axis, which indicates that the methods that have the lower planning times, they are the better. Our methods, which are green and yellow, maintain their advantage over other baselines, even if we increase the axis of variation. The CVA method is a conditional variation autoencoder method, while the Thunder method is another experience data-based algorithm which focuses on learning problem invariants. On this video, you can see the table motion planning problems generated with the same procedure. On the figure on the right, on the x-axis, you can see, on the y-axis, you can see the planning times, and on the x-axis, you can see how the planning time decreases as we add more experiences in the database. Now we tested how our methods generalize to different tasks. On the left, you can see a pick task where the robot starts from outside the bookcase and goes to pick a can inside the bookcase. On the right, you can see a place task where the robot starts from inside the bookshelf with an object rigidly attached to its hand and places it on another shelf. Here, we can see how training on a different task affects performance. The methods that are slightly shaded were trained on the pick task and tested on the place task, while the others were trained and tested on the place task. There is a performance hit, but not a very big one, which shows the generalizability of our method. Again, on the x-axis, you can see how the planning time decreases as we add more experiences in the database. Finally, we share our results in the real robot. On the left side, you can see the real robot experimental setup. You can see the Vicon cameras that give us the exact geometric representation used by Spark. And then here you can see the rays coming out of the sensors of the robot, of the 3D camera that is on the head of the robot. And these sensors are used, the representation we get of the environment is used by Flame. And this is the workspace description that we get for the different for the different sensors that we have. You can see that we are still able to achieve significant performance improvement even with Flame, which use a very noisy and partial octom. Finally, you can see an example solution from our frameworks in a pick and pack example. And you can also see the average improvement that we get over uniform sampling with Spark and Flame. With Spark, we get 3.4 times improvement, while with Flame, we get 2.6. Overall, we have presented two frameworks that reduce planning time in diverse workspaces, generalize to different tasks, and can be trained incrementally simply by adding more experiences in the database. Some limitations in future work include that the fact that we cannot transfer from one workspace to another. For example, if we train on the cell, we cannot transfer on the table. And also, the similarity functions are very conservative that we have, and they have to be designed by hand. Finally, our code, along with our experiments, our benchmarks, are all available online on the following link. Thank you very much.